Alright, so now we're going to start working towards proving our claims about characters. And the first step towards this is actually to prove a famous lemma that goes back to Schur. So in the one set of notes, this is actually lemma 2.13 in a section we're skipping, although there they stated at the level of algebras and modules over algebras, whatever those things are. But originally Schur proved it in the context of representations anyway, so that's the context in which we're going to state it. So let V and W be irreducible representations. And suppose you've got a linear transformation that is G invariant. Oh, by representations I mean G modules, right? Then either phi is an isomorphism, which means these are the same isomorphic G modules, which means it's a bijection, or phi is the zero map. Moreover, if we're working over over C, and V is equal to W, then phi is actually a scalar. So some scaling of the identity map. So for the first part, all you have to notice is that the kernel look at the kernel. The kernel has to be a submodule. Why? Because clearly if you look at anything, well, if you act on anything in the kernel, G dot phi of V is phi of G dot phi is 0. I think I got that backwards. Phi of G dot phi is G dot phi of V is G dot 0 is 0. So V for V in the kernel. So kernels are G invariant subspaces. V is irreducible, which means that this implies that either the kernel is all of V, which implies that phi is a zero map, or the kernel is trivial, which means that phi is injective. So let's work with this assumption. So we're going to suppose the kernel is injective. Now look at the image. The image is also a subspace, a submodule. Since W is irreducible, the image is either going to be trivial or everything. Well, if it's trivial, then everything got mapped to 0 and the kernel was everything, and we're not in that case, so it must be the case that the image is everything, which means that your map is surjective. So in general, if your codomain is irreducible, your homomorphisms are either surjective or zero. And if your domain is irreducible, your homomorphism is either injective or zero. For the second part, observe that C is algebraically closed, which means that from linear algebra, the characteristic polynomial for your homomorphism, because remember it is a linear operator between two vector spaces, so it has a characteristic polynomial, must split completely. In other words, if you have a polynomial equation over the complex numbers, it must have a solution. The point is, sigma has an eigenvalue. So we need this part because if you're working over real numbers, it's possible for linear transformations to have no eigenvalues, surprisingly enough. Now, it's not too hard to see that a scalar of the identity matrix is also G invariant. And so you can check that phi minus lambda I is G invariant. Only now you can definitely check that on at least some vectors, this thing is going to be zero. So this thing can't be an isomorphism. But it's G invariant between two irreducible G modules, and so it must be the case that it's the zero map. Whence phi is just a scalar multiple of the identity matrix, identity linear transformation. So here I is the identity linear transformation, not necessarily the identity matrix, because we haven't actually chosen a basis for V or W. What is this Schur's lemma good for? Well, we're going to bootstrap to see how this is used to study our inner product on characters. And so to get there, we're going to look at any G module V. And I'm going to show how the characters tell you about at least the trivial representation. So define V to the G to be all the elements in the vector space that are fixed by every element of the group. Notice that this is a submodule. It's invariant under the group action, and it's actually the largest submodule corresponding to copies of the trivial representation. And so the point is that it turns out there exists a homomorphism, a projection map, from V onto V of G. And this projection map is the averaging function. And remember here, G is acting on V, so G multiplying by G is a linear transformation. So here I'm going to put dot to remind ourselves that this is actually just left multiplication by G. We're going to claim that this is a G invariant projection map onto this subspace. And that, of course, pi of V of G is V of G. So it's very similar to what we did before with Maschke's theorem. It's the exact same idea. So you compute pi of h times any vector. It's 1 over g, summation over every element, g times hv. We want to get an h outside, so the cleverest way to do that is to cleverly multiply by HH inverse. Bring the H inverse inside the summation. And reindex the summation. Instead of looking at G, replace G with its conjugate. I mean, that's G prime now. Since you're summing over every group element here, it's still the same number of terms in the summation. So you still sum over every group element exactly once. So even though I do this substitution, I don't actually lose any terms. And so I do in fact get h times pi of v. So this linear transformation is in fact G invariant. Likewise, if you take a vector that's already in v of g, well, g dot v is v. So you're summing v times, so that's just scaling v by the order of g. That cancels out and you get v back. So this really does send pi of v of g to itself as the identity map. And so you see when you restrict pi to v of g, you get the identity. So that means that's eigenvalues 1 with multiplicity the dimension of v of g. Of course, by Maschke's theorem, we know that v decomposes as v of g, direct sum with its complement, and its complement is also G invariant. Notice that it's under the way this transformation works, this is a projection map. We can see that W must be the kernel. So yeah, this would be eigenvalue 0. With multiplicity dimension W. So with these two facts, we discover that the dimension of v of g is nothing more than the trace of pi, because the trace of a linear operator is the sum of its eigenvalues. And you're just adding up one dimension of v of g times, plus a bunch of zeros, which don't contribute anything. Well, you can compute the trace. In this case, this way. Now, finally, I have to point out the fact that we're really looking at a representation. So how do you actually compute a trace? Well, you compute a trace of the corresponding matrices, and finally you get a character. So what we managed to prove is that if you've got a G module, and chi is the corresponding character, then this summation is the dimension v of g. Based on our inner product formulas, it's worth pointing out this is the inner product of the trivial character with chi. Exactly as our formulas predict it's supposed to be, right? Because the trivial character takes on value 1, there's a hidden coefficient of 1 here. And what's that supposed to say about an arbitrary representation? It's the number of copies of that irreducible representation, and this is the number of copies of that irreducible representation. So we managed to get a special case of our general formula. And the rest of our work is going to be to see that actually you can get the whole general result just from this special case by working with a different representation and then applying this same result. However, I'll do that next time. For now, I do need to, as some preliminaries, I want to point out some facts about matrices over C that we're going to need. So we're working with complex matrices, not just any complex matrices, ones of finite order, which is not something we're used to dealing with. So because we're working over C, I already noted this means that the characteristic polynomial splits. Which means that the matrix does in fact have eigenvalues. Counting multiplicity. Moreover, from this equation you have a to the n minus I equals 0, and a deep fact from linear algebra tells you that that means that the minimal polynomial has to divide x to the n minus 1. The roots of x to the n minus 1 are roots of unity, so this tells you that the eigenvalues are roots of unity. But I'm going to give a different proof in a moment, in case you don't know what minimal polynomials are. The alternative proof is to just observe that suppose you have an eigenvalue and an eigenvector, just start doing the calculations. You're going to see all of a sudden you get lambda to the n v, that has to be equal to v. So intuitively, lambda to the n has to be 1. So if you have an eigenvalue with an eigenvector, then in fact the eigenvalues have to be roots of unity. There is one little gap here, and I think the notes kind of skip this too, is that how do you know this means the next claim? So the next claim is that A is diagonalizable. And so that's a result from linear algebra as well. The shortest way I can think of, so they're just citing results from linear algebra, but one thing I do know is that at the very least you must have Jordan blocks. And one thing you can check by induction is that when you compute powers of Jordan blocks, the diagonals actually are nth powers, but the upper diagonals are never 0. They're slightly off diagonals. You actually get a nice formula for them. And so the point is, since a to the n has to eventually be an identity matrix, this can't happen. So the only Jordan blocks have to be 1 by 1, just the eigenvalue by itself, which means you are actually dealing with the diagonal matrix. And then you have the fact that, well, a to the n, once you rewrite it as a diagonal matrix, is equal to I. Well, congratulations. Lambda 1 to the n dot 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 lambda n, or lambda k to the n, are all equal to 1s. Congratulations, each of these has to be a root of unity. So A is diagonalizable. Its eigenvalues are roots of unity. Also important, the inverse has complex conjugates as roots of unity. The reason why is because it should have the inverses as roots of unity, but the inverse is 1 over lambda I. You could always multiply the top and bottom by the complex conjugate. On top you get the complex conjugate, on bottom you get the norm, but roots of unity have norm 1. So that will pop up in the next lecture. Why do we need it? Because remember, our inner product actually involves complex conjugation. So these two facts are pertinent. The main one is that we're dealing with a bunch of matrices of finite order. And why are we dealing with matrices of finite order? Because we're dealing with a representation from a finite group to the complex numbers. So you know, any element has a finite order. And so it's, we'll say K. So its image is going to have order dividing K. So even though we talk about representations over the general linear group, the only actual matrices you can get are the diagonalizable ones whose eigenvalues are roots of unity.